Okay, so computer vision. We were talking about how to set up OpenCV and the last part on how to set up the Python libraries, to call the C++ bindings. Talk a little bit. I'm not sharing my screen. Share my screen. Okay. So you see my screen now?
Yeah, we do.
Okay. Just so you know, at the end of the class today, we're going to analyze. This is a dance video. Let me play it for you. So as you know, I work with a dance company. And we are going to try to analyze this dance video with machine learning and try to extract features out of it. That's why this is in here. So computer vision. We're talking about image processing. We learned a little bit about what are descriptors and what is each of them. How can we characterize items in an image, and especially how to learn how to compare those descriptors with one another, so that we are able to determine if two images are the same, to orient them and to put them together, or do some more complex stuff. We learned that there are a lot of types of descriptors. The oldest, or the original ones, are HOG, or histogram of oriented gradients, which use like a little bit of complex histogram description of the image descriptors themselves. But then little by little, people were working on this to make things faster, and we worked into binary descriptors, which are ways of generating descriptions of small patches of images, so that we can compare two images by comparing patches that have important characteristics. And that's where we stopped. Just to remember, and I will fix the format here. When you do image or analyze images by analyzing descriptors, you define how you are gonna sample the points around your descriptor. You are gonna compensate your orientation. For example, we saw that orb was a good descriptor that was using orientation compensation, and that was useful in case, or was an advantage with respect to, for example, brief. And also we saw that when you have a descriptor, you need to do a comparison between points, and that is how you sample the different pairs, so that you are able to build the final descriptor of your patch, and then be able to compare that to another descriptor of another image and see if they are similar or not. Today we are going to talk about video. There's a little part in here talking about homography. I'm going to just skip this for a little, but just so you that doesn't go unattended. Homography is just basically a way to transform and align the perspective of images. And for example, imagine that you take an image of this book on one side, on the left side, and an image on the right side. They have different perspectives, and you are able to compare by applying transformations on the image, on both images, finding points that correlate, and then orienting them to the same plane, let's say. And that's, for example, what you do when you scan documents with your phone, like with apps like Cam Scanner or things like this, that take a picture and find the corners and then orient it to the plane of the camera and put the document flat as if it was scanned on a traditional scanner, let's say. And the process for doing that, sorry, is called homography. So before doing that, before jumping into more complex things like what you see in this GIF in here, we're going to talk a little bit about video, and we're going to talk about how to capture video with OpenCV. Probably I want to say stupid things because very likely you know better than me about video, especially people like Benjamin that know a lot about video and stuff. But just a very brief thing, when we talk about video or when we have videos in our computer, we normally talk about a file container. So video is normally not only the video or the, let's say, the sequence of images one next to the other, but there's also like, it's a container of many things. And in that thing, you have, for example, the video itself, the audio tracks, and for example, any other things like, as for example, subtitles and markers and other things. Common video file containers are AVI, Windows Media Video, MKV, this type of things. Common video formats inside of that, or video codecs, are XBIF, H.264, etc., and that is part of the whole thing. And the audio can be codified as many other with many codecs, like, as you know, depending on whether or not they lose or not information, like MP3, FLAC, IF, AAC, Windows Media Audio, etc. But yeah, so if we clarify, and the thing is that video is, when we talk about a video file, we just don't have a video inside, we have video plus audio and other things probably, and they are separated inside a container. Important is that OpenCV likes AVI, so AVI file container, and that is not the only one, but we will see that when we try to load videos in another codec or another file container format, we will have to use external readers, and that probably will slow things down. But OpenCV likes AVI, so if we can use AVI, better. So let's start with some code. We are just gonna do a very quick example on video itself, and this is the one. So as you see my code right in here?
Yeah.
Okay. So I'm going to turn off my camera so that OpenCV can use it. So let's just open this. Very easy. The only thing that this is going to do is just open a window and show the image capture from my video. So Python 05. Let me just put this here. Okay. Here. Okay. And here. And like that. Okay. So now, well, I just run this script. You see the output. And here, the only thing that we did is import OpenCV, open the video capture. Video capture, there are different devices on your computer, and they are ordered by targeted, like start by 0 for the embedded camera, then an extra camera would be 1 if you have 2 cameras on your computer, and the extra camera would be 3, etc., etc. So I'm opening 0 because it's the embedded camera in my laptop, and basically I just have a while true video loop in which I'm gonna read one frame. I'm gonna put it in the in this window, and that's it. If I press Q, then I'm just gonna exit and kill everything. So that's pretty much it, what it's doing. We could add something else, for example, to write that frame whenever I press a letter or a key. So for example, if I do like this, and I say frame, frame, I put S in here, and I say frame index equals 0. So I'm gonna be putting a different frame every time. So every time I press save, I'm gonna save a different image. So like that. So now what I should be doing is that every time that I press S, I'm gonna make like a capture of the video, and I'm gonna save it to a file in a folder that I'm gonna call capture, and then it will be the name of that image. It's gonna be frame and underscore and the index of the frame. So I'm gonna make the folder capture, and then I'm gonna execute this Python again. So in principle, if I do S, every time I'm pressing my letter S, just so you know, because you cannot see anything. And I'm gonna press Q. If I go to capture, LS, and I say open frame, there we go. So here we saved an image that was the screen capture at the moment when I press letter S, and that's it. The only thing that I forgot and is that I was overwriting every time. So frame index +1, because I was writing all over and over on the same image. That's why I only have one. So if I do that again, Python, very easily. So I press letter S. I don't know, I'm pressing it many times. And now Q. Probably I even clocked my computer. Let's see the capture. LS. I have, I don't know, 13 frames. And in here, so I have all the screen captures. So that could be, for example, a way that you could programmatically, not by pressing a letter, but for example, when something happens, that something counts, for example, the reading of a sensor or a button in your Arduino, or something gets triggered, then that you take a picture of the capture. And this, for example, could be the easiest or the simplest security system in the world, that you have a camera with a Raspberry Pi, and anytime that you detect motion in the video, that you save that picture and you see whoever entered your room, for example. And that could be the the simplest safety feature of your apartment. As you see, it's like with extra spaces and everything, is 21 lines of code. So it's very, very simple. Now let's start doing a little bit, or let's start talking a little bit about what can we do with that video to detect things on it, or to see what we can do with those frames. And for that, I think that a good example is to start tracking movement, movement or identifying things in videos, let's say in general. So let's rephrase this a little bit. How can we? Probably this is an open question for you. What would you do if you had to identify in a video a person and track its movement? What would be the workflow that you would follow?
So basically, we will capture like the first video and then minus this by the next like sequence, and then we realize that somebody, like some pixel changed, so we can understand somebody moved. No.
Okay. And how did you know if that what moved is a person?
I guess it depends on a silhouette. I mean, it's kind of like a edge detection to know.
Yeah, I would guess it's related to what we learned last time, which is edge detection, and then what we did with the psychopath eagle.
Okay. Any other ideas?
Also, you need to make sure the camera doesn't move, I guess. So you need to compare to the local pixels. They're like we did with the orientation thing you said.
And what about brightness, for example? If there are lights and these type of things?
Probably shadows around them, or
maybe you could check the amount of pixels that change in every cluster and then compare it to what a human could be.
So those are all very valid answers. We're going to go from the simplest of the simplest and then try to make it to the more complex or more recent of all of them for video. So ultimately what we want is to detect, first identify that there's, for example, a person in the video, and then learn or get to or know where the position of that object, in case a person, is with respect to the frame of the video, let's say. So for that, we have to do two things. First is do an identification, so analyze the frame and see if there's a person, or in this case. And secondly, find where that person is and find the bounding box that contains that person, and for example, get whatever we want, like a centroid or the bounding box or the silhouette or something like that. So one of the ways we could identify the one object, and is probably the simplest one, is by just finding the color of that object. For example, I have this, I have my phone. I'm gonna put on the camera back again. My phone has a very distinct color, and I could just try to find or track the movement of my phone by just filtering the image and say, okay, in each of the frames that I'm capturing, I'm gonna eliminate everything that is not of the color of my phone. And I'm gonna calculate the centroid of that based on the captures that I'm making and the elimination of everything else that is not color.
Maybe you should change your code.
Exactly, that's what I was gonna say. That in this case, that is gonna be a little bit tricky because my code already is a source of error, and we will see that that is not the best technique to do these things. But sometimes, and this by the end of the session, we will realize a little bit better about this, is that this is going to be much faster than doing anything else, because color is the very first information that we have in the image. Is basically how the information is stored in the image. So we can just do a very simple operation. And that, for example, is what you would do, for example, to eliminate the background on video. You have a very distinct color in that normally is called like a chroma or chroma key. And that could be a very bright blue or very bright green, yellow, pink, these type of things that is going to be not found in the objects that are in front of the chroma. And then just eliminate that part with high resolution. And that's how you do it in movies, how you do it in many other setups. For example, even Zoom, I think does it now when they blurs or eliminates the background and changes it. So let's see an example for that, and let's see how would we do it. So let's stop the video again. And now, why do I have, okay, like this. As usual, let's run the code and then we will see how it works. So Python 06 color tracking. In here you see that there's some extra stuff. By the way, all this is not my code again, and not all of it at least. I modify code that I take from examples online, and OpenCV is a very good resource for this. But you see that in the bottom part, there are bars that correspond to the range of HSV color code for detecting in my image. So you see that right now, when I'm detecting something that is within the range of colors that I have in H range, S range, and V range, then it's going to be painted in white. As soon as I reduce that range, for example, I go here and I reduce it, then I am reducing the range of colors that pass, and the colors that pass are painted in white. And then in here, I'm calculating the centroid, so the center of gravity of that image. That's why you see this blue circle in here, because it's somehow the resulting center of mass of the white area that you see in the screen here. So let me just cheat a little bit and see how HSV works. I think I had it in here, but probably I removed it. Color detector, no, HSV. Just to clarify. So like this. So we are talking about hue, saturation, and value. Okay, and these three things is what we are touching. Basically, we have to adapt the ranges so that we are able to detect the red of my phone. So that's what we will do. Luckily, I cheated a couple of weeks ago when I did this code. So we have a little cheat list in here, and I'm just gonna set that up. So this is somewhere, let's put the phone in here. So right now we are not detecting it. We're gonna put it around 0 to 6. S is around here, and value is over down here. Right now we don't see anything. No. It's a little tricky to find. Value. Oh, so we're on the other side. No. It's invisible, my phone. Okay, so we're looking into that area. More or less. Almost we found it in there. Okay. So you see already, as you predicted, that my code is interfering with this. And if we look at the video, now I'm able to find the position of my phone or tracking the position of my phone just by tracking the color. But as soon as I lose the phone, I'm finding my code. So this range is a little bit stupid, but the example still applies. So the idea is that just by doing this with the color, it's very simple already and very fast. You see that this still is running at 60 frames per second, and we are not losing any information. For example, with a machine learning algorithm, you wouldn't be able to do this because the algorithm that we're going to see at the very end for 720 pixels of video quality takes around 2 seconds to analyze each frame. And if you are doing that at 60 frames per second, then it means that for 1 second, it will take you to work it out at like 2 minutes. to analyze one of them. So it's not that simple to do that, right? It's in the chat where to how do you detect everything but the phone, then just invert the image? Okay. We could probably do that actually, to import the image itself. Let's see how it works, and maybe we can do that actually. So, do you see my code? I'm gonna stop this. Well, actually, I'm gonna leave it. So maybe I can do this like that. So again, we're importing OpenCV. I don't think we need this actually. Oh yeah, we do. We could pass an argument, but that is something like it's not very important at this moment because we are just capturing for the device 0 in my case, which is the camera, but you could pass another camera if you wanted to. Here we are defining some things for the track bars, let's say. So for these bars in here for the high, low, etc. And these functions I will explain in a second. They are just basically callbacks for when a value changes on the track bar, so that we do something every time that we change it. And basically what we are doing is just limiting the possibility of the track bars to not go to, let's say, to not cross, because this low H is the minimum hue that we want, and the high H is the maximum hue that we want. So we are looking into the range of hues, let's say, and we don't want the high to be lower than the low, and that's simply it. That's the only thing that we are doing in this callback. So basically, we already know this. We're capturing the video. We are making two windows in this case, one of them for the object detection and the other one for the video capture. And we are creating the track bars, and we're giving them a name. We're putting it in a window. We're putting the minimum and maximum value, and we're assigning a callback. This could be just nothing, and then nothing would happen when we move the track bar itself. You could just put that into a callback that does nothing, but you have to put something. For example, we could make a function that is nothing, that takes nothing and does nothing. And then we do this, and it still works. Okay. And then once we have that in an infinite loop, we're going to capture all the time the video, and basically for each of the frames, we have to do something. And this is where you have to be careful, because if you're reading at 60 frames per second, and for each of the frames you do something that is very long, then you're going to have a difficult time identifying things. And that we will see that in these cases, less is more. So not because you go to an artificial intelligence model, you are going to do better, because an artificial intelligence model is much slower than what we are doing here, which is just comparing numbers one to another. Okay. So basically we say we have a frame in RGB, and we're going to convert it to HSV with this function, CVT color, which is receiving a frame and a color format. So that outputs a frame in a hue, saturation, and value format. And then we're going to say, give me the frame that is within the range of H, S, and V from the track bars that I have from the variables in there. So I'm just saying, with this function in range, I'm sending the image and sending 3 low values and 3 high values. And it's giving me back an image that is white whenever that matches these conditions, and black whenever there's not those conditions. Then we are cleaning the image a little bit. These two are noise subtraction and elimination from the image itself. And finally, we're calculating the moment of it's called moment, but it's like basically the center of gravity for the image itself. So for the white part of the image. I don't know if you know more or less, I think we talked a little bit about this, about moments and center of gravity. Is this clear more or less? The centroid concept and center of gravity and this type of thing? Yeah.
Is that what you showed about the triangle and the direction of the objects depending
Yes.
of the centroid?
Yeah, exactly. Yeah.
I have a question. When you are cleaning the image, I was experimenting with the Gaussian blurs, and it seems that it doesn't work the same for every image. I mean, if I change what you usually have in 3 by 6 or 9 in sometimes when I was trying to run the code, it told me there was a mistake. So I changed the code again to 2 or 3 and it worked.
Yeah, I think I'm not fully sure about that. We would have to do a little bit of research, but I think that in not all the cases the matrices are implemented or the kernels for the filtering, and that is related a little bit to I don't know from last time if you remember this, but it's the Sobel kernels. That are that are mainly matrices that are defined by a 3 by 3, and that probably uses the same concept. So probably you could reduce that the size of the filter, but not all the sizes are probably implemented, and that's why it will give you an error. So it's not like you incrementing the size of the matrix will give you a bigger or smaller blur. Means that these kernels in there are probably not implemented for every size that we want. And I'm not saying that the Sobel operator is the one that we are using in the blur, but it will be something related to that.
Yeah, I thought that maybe it was because of the amount of it was not a multiple of 3 or 4 or the number I decided, so maybe it was confusing for you to do the operation.
Yeah.
I wanted to ask something else. I don't know if the code you have it's the same that we downloaded, because in one of the examples before, the camera, video, and capture, when I run it, it runs my camera flipped. And it seems that you didn't have the instruction flipped in the one you have. And in this one, when I'm running it, the operation, well, the other window, it appears all white. And when I zoom, it appears with a full of squares saying 255, I mean, white. But I'm not sure why. So
in the capture video, I think that depends a little bit on the machine and on the format. I'm not fully sure about this, but I know that this is an issue, that sometimes you have to flip the image. And that's why in this example, in 05 that I skipped, you have this flipping here. And probably, I think it depends on the hardware on the OS, that sometimes you have to flip the image just by the way that is defined, probably because it has some mirroring effect or something else. I'm not sure about this, but I know that there are issues about this thing. And regarding the other one, that I don't know specifically. Probably we can have a look into it afterwards if you want, or now, up to you.
Yeah, don't worry. I think maybe it's because of the OS, because I have Sierra 10.12, because it's the best one I can get with my graphic card. But it might be because of that.
I have a like a very mediocre graphics card, and it's still like I can get to do some little things. Well, not little things. I can do quite a bit of stuff with OpenCV. So it's like it should be probably fine.
Okay, I'm gonna research a little bit, and I'll let you know if it doesn't work, because until this moment it's the only exercise that hasn't worked well.
Okay. Okay. So that's that would be it. If we, for example, want to do the opposite, maybe what we could do is, as you say, try to flip the image. So, well, here, bitwise not exactly. Bitwise not frame. And let's see what happens. So we're here, quit. Then we'll run this again. Up. And we will need to actually do this in here. And sorry. Like that, okay. And image. Okay. So I think that should work. Let's see. Yeah. So we're still in the center. Okay. Let's remove this. Okay. On low. Let's try again. So we go around here. It doesn't take my mustache. That's funny. So that's my phone, and it still finds it. So probably I'm doing something wrong. Very likely, of course. Something like that. So it still finds my phone. Okay. Well, let's not waste too much time in this. But as you say, that probably the easiest thing would be just to invert the image and find in the black and white image the centroid of what the font is. And wait, that's it. I didn't actually change anything. I just calculated the image, but I didn't do it. Let's see again. So here, more or less over there. So now it's ignoring my phone because we are finding the centroid of everything else but my phone. So it doesn't actually matter much if I move because I am very little with compared to the background. And you see that now we are like, we still have the phone in here, but we are basically just ignoring it in the image. So if the phone moves, the centroid of the image itself doesn't modify. So you could do this in like a way to, for example, have markers on your on a camera, and then make them like a way to always have a reference system of your camera, no matter if they move, for example, because you ignore whatever is going on except the markers themselves, and that way you can always orient your camera system and this type of thing.
So that's a way
that,
to ignore the environment, for example, in an animal nightlife image detection system, like to know if a tree moves, but I already have it tracked, so it won't detect the centroid of the tree or something.
Yeah, something. It would be, that could be, for example. Yeah. Okay. What else? So that can close. Now we know a little bit how to that basically we are tracking movement just by tracking color. Another way that we could detect if things are moving is something called optical flow or optic flow, which is basically, as Armand was saying, making the difference between two images, the frame X and the frame X minus 1, and basically identifying which of the pixels have moved and then drawing a line between the pixels that have moved. And that, for example, is, I think, is represented in this tutorial, and we will do an example. Basically, you are able to track where the positions of the pixels were and if they have moved in a space in one image. For that, there's a little bit like of processing to do, but that would be more or less the resulting image in this case. There are two ways of doing optical flow. One of them is the dense optical flow, and the other one is LK or Lucas Canade optical flow. But as far as I know, and I'm again not a super expert in this case, is that in the dense optical flow you just calculate the whole image. In the LK one is that you only calculate key points. You identify key points first and track the movement of those key points, not of the whole image. And we're gonna see the difference in an example. So for example, in the case of optical flow, let's run the example, that one. I think that that's gonna open my camera somewhere, exactly. So it's painting it in a very psychedelic way, but basically is calculating the difference between each of the frames and putting that in RGB scale. So if I move, you see that this is much slower, but it's painting what has moved, and the rest is static, so it won't represent anything. If you have a good graphics card or better camera than mine, you will find that this is much easier, especially because when I do this, now the background moved, but my camera as well adapts to brightness automatically. So whenever there's a brightness change, there will be a pixel color change, of course, and that will imply like there was a movement when there was nothing moving. And that is a little bit difficult to compensate just by looking at the pixel color itself and not about any shape or anything like that. But as you see, well, this is a little bit slow, but still you are able to know where things are moving, and but it, of course it's very subject to noise in this case. So open frameworks implement a way to do this, and it's called optical flow. The same, we open the video capture, we do a while loop, an infinite loop, and then for each of them, we read the frame, we send it to gray, in this case, and we map the difference between the previous frame and the current frame to these values. And then we do like some sort of normalization so that we are able to see small changes with respect to big changes, and we put that into a color, and then we show that image. Okay, so that's basically what we do in here. Basically, here we calculate the flow, then we map it and normalize it, and then we show it in an RGB image again. And that's pretty much it. And then also if you want to play, since it makes a very cool images, you can, whenever you press S, it will save the image itself, and you can maybe print it and get rich like Andy Warhol or something like that. And then let's see the next one, the optical flow, but a little bit more advanced. And we will see that this one is a little bit better because it tries to find key points and doesn't calculate the whole image each time. So it will try to find, okay. Okay, so let's come back to the phone. And you see that there, not very good, but it's finding some key points or some corners on my phone sometimes, and is able to track the movement. But you see that is, of course, it's not perfect, because what we are doing is trying to find edge. You're doing the same, Pablo. So you're doing, so you mimic.
Yeah. I'm playing.
Okay. So in this case, what we are doing is trying to find distinct edges in the image and then tracking the movement of them. And as soon as we find something close to the last position of that edge that was as well similar, yeah, it's to my nose now. My mustache is distinct, that's why. That's very cool. So here, let's stop it. So here, what we are doing is tracking corners in the image or edge or the distinct elements in the image. And of course, when you are analyzing pixel by pixel and getting the corners, at some point, probably the corner that you have in, so it again. So if you have the video and the corner that you have here from the phone to the background, all of a sudden becomes very similar to the corner of my face to my headphones, or my face to this brightness in this size because of the light. And then we start tracking that instead. And of course, that is not the best way of tracking movement. But if you have a static image, like for example, in a highway and there are cars passing and there are not many changes in light, for example, you are able to do this type of thing. Of course, you can also try to play a little bit with the parameters. But you saw especially that this was much faster. Why? Because we are only trying to find important elements in the image and then tracking the movement. We are not tracking the image, the movement of all the elements in the image. We're just tracking the movement of some very little ones. And we are putting a lot of time or effort into detecting things, but not to track the whole differences in pixels. Do you have any questions about it? No. Okay, I think if you like this one with tracking my notes, you will see the next example. It's gonna be much fun. So where was I? 2020 computer fish. Okay. So now we see that one of the main issues in here is that we need to be able to process faster than we capture. And that is kind of obvious, but if you don't have a fast enough processor so that for 1/60th of a second, you are able to process the whole thing, then you cannot capture at 60 frames per second. You have to reduce the speed at which you capture. And that implies that it's very important, especially when you're talking about small processors like in your phone, to optimize the algorithm. before we jumped into the latest development on video processing, let's talk a little bit about how you do to detect, for example, faces in an image, and also how you are able to do that on video. So the principle of this is that we are able to, instead of making a very complex decision, for example, I take a picture and I decide whether or not it's a face or not, I'm gonna make very small decisions and just do like very small, simple decisions. And if the first decision that I take is not, let's say, validated, I'm just gonna say, no, this is not what I'm looking for. And I'm better gonna represent that with a little bit of whiteboarding here. So imagine that do you see the whiteboard? No.
Yes.
Do you see it now?
Yeah.
Yes.
Okay. So imagine that we want to detect a face, okay? And we know that a face is more or less like this, something like that. Very simple, but let me find, how do I change the color here? Okay. Format here. So we know that a face is made out of different elements. You know, we know that almost all of the faces have a very dark area in here, that is the eyes. We know that there's a vertical area in here that is probably darker than this area or this area. That next to this area, there's the area of the eyes. That next to this area, there's the area of the mouth. And we're gonna start trying to make decisions based on that composition. So what is the easiest way that we could determine whether or not this is a face or not? So imagine that we build a system in which we input a face, a picture of a face, and we are able to run the processes that we were talking about the other day. So analyzing the images by small regions or patches, and decide whether or not that could be a face or not. If we make a decision, an initial decision of what a face is, the most distinct element of what defines face, and we don't pass that decision, then we don't try anymore, and we just go to the next region. So for example, we go here and we say, is this a face or not? Does this have one element of a face? No, then we ignore it. Does this one have an element of a face? No, then we ignore it. Then we go on, and then we arrive into here. And we say, does this have an element of a face? Yes. Okay. Then I'm gonna stay here. Does this have an element, another element of a face? Yes. And another one, and another one. And then I'm gonna, by deciding, making those small decisions, I'm gonna make that area a little bit bigger and say, okay, does this combinations of area have these elements of a face? Yes. And then I run the whole thing again. And then I go to the whole thing and I say, okay, does this have all the elements that define the face? Yes or no? How do we make all those small decisions? So the funniest thing
like
is
playing battleship. Like, is there a ship there? Boom. Okay, next to it.
Exactly. So how do we do this? So you remember that we were talking about convolution. So it's basically that. And it turns out that one of the easiest way of saying, or one of the shapes that could help you determine whether you have a face or not in there is by imagine that this is filled in black, by passing this filter and analyzing the result of that filter in each of the regions of the face. If that passes, then we're gonna go to the next one, if this is a yes, and we're gonna run. I'm making this up, a convolution filter that looks like this. So this is black, white, and white. And the same. If that passes, then I'm going to go to the next, and I'm going to run the next convolution filter, and I'm going to decide if the test passes or not. If not, I just say no, and I drop that region, and I forget about it. So you are taking very small decisions in some sort of what we call a cascade, and that's why what we are talking about here is cascade classifiers, or in general, hard cascade classifiers are very common for these things. And basically, what they do is what this shows in here. So imagine that we have this picture of a person. We're going to start analyzing in each of the regions of the image, and we're going to make a lot of decisions per second, checking for these very simple features and seeing if they pass or not. That the test that we're running and that we have defined that better define what a face is, okay? And you see that we are skipping a lot of them, but sometimes we are stopping in some areas. So let's skip this a little bit and let's get to the interesting part. So we see that as soon as we get into this area, we will see that the number of tests that we are running is much larger, because we found that some of the most basic tests of what a face is, of what we can define as a face, pass. So we can keep on iterating within the cascade and keep on checking whether or not that is a face or actually or not. We're going to stay there, and we're going to try to make that area a little bit bigger to keep on testing. And you see that now the classifier still stays there, and little by little finds more and more features. And you see that all the faces, whether you're ugly or very pretty, have the same shape more or less, which is a vertical area with different brightness, and a darker area in the area of the eyes, and a darker area on the area of the mouth. So if you are able to run this process by just deciding on very simple things, whether or not there's a face or not in there, and avoiding to analyze the whole thing, for example, as we did in optical flow, then you will be able to determine that that's a face or not. This is called Viola-Jones. This process is a research paper. I think is quite oldish for what the state of the art is. And I recommend that you watch this video, and if you don't follow this YouTube channel, that you start following it, because it's super interesting about algorithms and electronics or computers in general, which is called Computer File. And this guy explains very much better than I do the process of a cascade, what a cascade classifier is. But this is, if you think of it, this is 2001. And this algorithm is used, for example, in all the algorithms that your phone uses for detecting your face with the camera, Facebook algorithms to detect whether there are faces in images for you to tag them, etc., etc., etc. And is as simple as defining small features that say, okay, this feature defines the area of the nose. This defines the combination of the nose and the eyes. This defines, I don't know what else, and running these little tests and saying, okay, this is similar, yes, then I run the next test. This is similar, yes, and I run it. This is not similar, no, I discard it. Then this is not a face. If I am able to say all the tests of all the classifiers have passed, then I have an image. I have a face, sorry, in my image. If not, I skip it. You can read a lot about the algorithm, I'm sure, but let's go more towards the code. I guess that you still see the whiteboard, no?
Yes.
Oh, okay. So sorry, I was showing Well, you saw the video, right? Or not? You don't see a video?
I shared it in the chat.
Yeah, we didn't saw it, but Danny shared it on the chat.
Okay. Okay. Well, the video, but that was the whole point. I thought I was showing a video, but this is what I was showing. Probably now this makes more sense. So each of the red squares that you see in there is the patches that we are analyzing. And you see that the little kernels that we're trying are these black and white little kernels, and they are taking the decisions of whether or not those are features that describe a face or not. And you see that at some point we're going to stop on top of the face and start this spending more time in there, because a lot of tests are being passed in that area, because a face is defined by what we say, like a brighter or a different color area in vertical in the center, and the eyes and the mouth, etc. And we see that in here. Now we are spending a lot of time because there a lot of tests have passed. And when all the tests pass for these individual very simple features, then we have a face. And that's what we are doing in this video. Probably this makes more sense now. And again, this video under here, computer file, is what I was saying. That is very interesting as well if you want to see it. This guy explains the algorithm much better than I do. And just to finalize, this is based on the Viola-Jones algorithm, and using these little features on the right side to determine very simple tests and analyze whether or not there are features that identify a face. And the important thing about this is that you can run this very fast, real time, and for 20 years, there hasn't been any other algorithm that has improved this performance, and that is why you are able to do this, for example, in mobile phones or small processors to detect faces. And if you are able to do the same process that they did, but for example, for identifying pigeons, for instance, then you will have the cascade classifier for pigeons, and you will also you would have a real-time processing algorithm for this, based on something very simple, which is taking decisions, very small decisions, and discarding very fast things that are not actually fake. So let's do a test. Let's stop with the talking. This is a camera. With a camera, sorry, and this is number 7 classifier. Let me turn off my video. I think you're gonna love this one. Classifier, it's opening. There we go. So it will paint in my eyes. Actually, let's put it in here. So if I go and look into the camera, there you go. It's finding my face, and it's finding both my eyes, and it's doing this almost real time. Of course, I look very ugly with that in my face, but you see that the algorithm is able to track in real time or almost real time where my face is by running this simple test in each of the frames. And that's it. So let's have a look into the code. Again, we take open frameworks, and we call this cascade classifier, and we define 2 classifiers, one for the eyes and one for the face. We open the camera, and for each of the frames that we capture, we run this function called detect and display. And what does that function do? It turns the image into gray. It sort of equalizes the image histogram, so more or less makes it 2 bright colors, it puts them into not as bright, and 2 dark colors, it puts them more or less uniform, so that you don't have very uniform or heterogeneous image. And then basically sense the things, sense the face. So the classifier detect into that frame, and we return a number of faces. And basically, in this for loop, we draw a circle that has the center based in here. We draw it on the image, and we put this color and dimension. And the same with the eyes. Finally, we saw the image, and that's it. So the important thing about this is in this function, and that is what it makes it really fast, which is the implementation of this classifier itself. So for example, now you could not only do this with a video, for instance, but you could do this also for an image. And of course, if you just send an image to this, then you are able to identify where there's a face in there. You're not able to know if who is that person. To identify persons, you really need to go to machine learning, but at least you're able to know if there's a face, and if there's a face, where that face is. And this gives you the coordinates with respect to the coordinate system of the image of where the face and the eyes are. And for that, you can then start doing tracking and making things that react to one another and these things. Okay, do you have any questions so far, or?
Daniel always has questions in the chat though, for some reason. He never talks.
Oh, okay. Hello, how is the technical science in the letter? Oh my God, how do you define these classifiers? By the way, just running through the images and remembering which tests work there. Yeah, what these people did, these biologians, is that, I don't know exactly what are the names, but Paul Viola and Michael Jones, yeah, they basically took a lot of images and they ran a lot of classifiers on them, trying to better define the simplest classifiers that better defined the set of images, and no matter what type of images, and came up with a set of the, like, let's say a cascade or a decision tree that better could define which one of them was the set of classifiers that was describing what a face is, basically.
So does machine learning kind of like basically figure out classifiers to then use later?
Exactly, yeah. The thing is that machine learning somehow does that by itself, by training the algorithm. Deep learning is able to group those classifiers into more complex things, starting from small things like, for example, an edge or a corner or like a circle or something like that, and then making that into something bigger, for example, the tip of your nose or the corner of your eye or a little bit of hair, etc. And then that gets joined into something else and something else and something else, a little bit bigger each time. And each of the layers is what defines the depth of the neural network. And that's why if you want to be very precise, for example, to not only define if there's a face, but to know if that's Antoine or Benjamin, then you have to be able to make these combinations of little features into something a little bit more complex, because you both have two eyes, you both have a mouth and a nose, and sort of similar like hair color, skin color, etc. But of course, you don't have the same face, and the joint, or like how those features are combined, is what defines your face. And that's why you need to go to more complex algorithms like machine learning to be able to distinguish Antoine from Benjamin. You could, for instance, just have always one picture of Antoine and saying, is this picture of Antoine similar to this other one? And you could, for example, with what we've seen, make some sort of classifier that says, okay, it is, but it will be dependent on many other things. And that's why we looked into descriptors and these things. But at some point, changes in how he has his hair one day, or how the picture was taken, if he was tired, if he's looking to the side or he's closing his eyes, etc., are going to define different features, and they're going to give you false negatives. For example, they're going to say that it's not Antoine when it's Antoine, or the other way around. And that's why you need to go to more complex things. And for that, you need to go into deep learning.
So it's that, are those the arguments you add in the parser add argument in some?
No, no. In this case, for example, what I'm doing, and we will see that those arguments, for example, are the ones for YOLO, which is the last algorithm we're going to see today. But in this case, is whether or not we are going to have well, which camera we're using, and what is the face and the eyes cascade. The cascade is basically the set of little tests and where that file is in my computer, basically, to define, let's say, the file that will describe those tests. And this is basically this file. We could open it.
But I need to already have that file set up with the
Yeah.
okay, yeah, because I also tried to open it and it was like we cannot find Óscar computer.
Oh, sorry. Yeah.
Don't
Actually,
worry.
that is stupid of me. I committed my path in there. Well, that's fine. So yeah, but here you see that is defining the different stages, and each of the stages have classifiers defined with, I don't know what these nodes exactly mean, but that's basically the shape of the descriptor. And you go one by one, and if you get to the end of the list, that means that the classifier is successful and that is a phase. If you don't pass all these tests and you get around, you stay here, then you go to the next area of the image or to another image, for instance. Okay.
And where do you do this test, or how do you build this classifying? It's that by,
well, that's the
lot of images.
Yeah, exactly. But you also have to try defining descriptors. For example, for images, for faces, it makes sense to have this type of features that have very simple things like vertical lines, horizontal lines, etc. But if you have more complex faces or more complex things to detect, then you might be willing to try with different features or image or tests. And for that, you need to build your own features and by iteration, and that's what these guys did in 2001.
But is it a process of me defining the features or loading, I don't know, a lot of apples into a system and it generates the XML?
Well, let's not. Okay, we're in a very difficult frontier here. So this process is okay. Let me go back to new share here. Because I think there's a critical difference in here. Do you see the whiteboard?
Yes.
Okay. So right now we are in the field of machine learning. And there's the other field of deep learning. Deep learning is inside machine learning. It's a subtype of machine learning, but we are not talking about machine learning at the moment. About deep learning at the moment, sorry. So what do we do in machine learning? In machine learning, or in this case, what we're doing is we take an image and we're going to run an algorithm that is somehow predefined. And in this case, this algorithm is what we call a decision cascade or a cascade classifier, which basically is taking small decisions in each of the images and basically only deciding that something is a successful decision somehow, or a successful identification when we have passed all the tests in a sequence. And that's what we define in a file, in this case, an XML. So the process of defining how that file looks is what you have to do when you design the algorithm. And in here, you input two things. One is knowledge, like personal knowledge. Like, for example, I know that faces generally have two eyes and a nose and one mouth. And there are very many faces with two noses. And that is something that you know from the physical world. And the other part is how do I decide which of the tests and which order is the best? Just by iteration and by trying. And since a computer can do that for me, I will send, I don't know, 40 million images inside and define which of the sequences best describes where our images are not. And in that process, I need both inputs, and I'm gonna get one file that defines the sequence of what I'm doing. And it's important that the concept of sequence, here I am defining a series of steps and a series of decisions. If one of these decisions in here in the middle is null, then I get out and that's it. I don't run anything else. In deep learning, you do something different. For example, you will take an image. You're gonna run things onto the image, like, for example, a convolution filter on top of the whole image, and you're gonna, for example, take your kernel, take this patch of the image, run it through that kernel, and you will get another set of numbers. So this goes in here. And then you have another kernel. And then you will get another set of numbers. And then, so this is image one. So this is the original image, for example. And this is the result one. This is the result two. And we go on and on and on and on, okay? What we do in this process is that after a while, this image might look like a vector because we applied so many operations that this, instead of having columns and rows, it's only columns. And this we can compare to another vector and say, okay, does this vector look similar to this vector? Yes, then I have a dog. No, I have a cat, for example, or I have no dog in this case, no? But the important thing here is that when you run this process, you don't define this sequence. You feed this algorithm a lot of images of dogs and a lot of images of cats, and you tell the algorithm, these are dogs and these are cats. I want you to learn how to define this comparison and these kernels by yourself. I'm not gonna put any knowledge by myself. You're gonna do it by yourself. And you are gonna optimize these numbers, however many millions of numbers that are there, to better decide when there's a dog or not in these pictures that I give you. And for that, I'm gonna train you. I'm gonna give you a lot of images, and I'm gonna tell you in which of those images there are dogs or not. But I'm not gonna tell you what you have to do. You are gonna decide these numbers and these operations by yourself. But every time that I give you an image, you are not gonna have a decision tree in which you, as soon as you decide that that is potentially not a dog, you are gonna go out. You are gonna run the whole thing, get to the end, and there you are gonna have a set of numbers. And if that number looks like a dog, or is like what we consider that a dog is, then we're gonna say that that's a dog. And if that doesn't look like a dog, then we're gonna say that is a cat. But I'm not gonna decide, or I'm not gonna give you anything else than just images and an overall structure of what these operations are. But I'm not giving you anything else like this more like intelligent workflow in which as soon as you decide that that is not the dog, we just skip it and we don't waste resources. Okay. The advantage of this is that this can grow endlessly, because here the only limitation that we have is the amount of numbers that we can store in our computer and basically in our RAM or GPU, and the way that we can process them. And as soon as you have a lot of GPU power and a lot of memory to process this fast, then this becomes very easy to grow. And then that is more or less why you have a lot of deep learning algorithms lately, because GPUs have become more and more affordable and they perform much better. And you are able to make more complex decisions because basically you are making a very, very big version of an algorithm that you couldn't make yourself, because it will take years for you to make millions of operations like that. Not only doing the operations itself, but deciding which operations you have to do. What you just let the computer do is, okay, we're gonna do these simple operations, for example, convolution, and the kernels that we put in there is what the computer is gonna decide. We are not gonna tell him to use a Sobel operator or a Kalman operator or whatever. We're just gonna say, just do your own and decide and iterate over so that you can find the best. And the idea is that since you have a lot of them, a lot of those kernels, then on average, we're going to be able to tell things off or apart, because basically we have a lot of single items making decisions.
The logic in the deep learning, does it only stay in the deep learning, or could you kind of export the logic so that it can be used on the left, like XML, like into?
Exactly, yeah. So at the end of the day, what you have is, in here you could have two things. One of them is an algorithm. So basically saying, okay, I'm gonna run, imagine that I say, okay, I'm gonna run 1,000 convolutions, so 1,000 convolution stage. And then in here, I'm gonna make an algorithm that is called the FAB algorithm, that I also have some parameters to train. And then I'm gonna make another 10 million convolutions. I don't know, I'm making that up, with kernels that look like a rectangle with, I don't know, with some restrictions. And the whole thing is the magic of like the structure of the algorithm. That is one feature, so that is the algorithm itself. And the other thing is that of those 1,000 convolutions, there's other operations that you do in the FAB algorithm, and in the 10,000 convolutions that you do at the end, all of them have its own kernels and its own little operations that have to be stored somewhere. And that's what we call the weights. So each of these that we could see, for example, this as a node. So each of these operations are taking, this is one weight, this is another weight, another weight, another weight. And there's a kernel in here, a kernel in here, kernel in here, or a simple operation that is multiplication plus sum or things like this. And you could take an image, put it into, for example, I don't know, the red channel in here, the green channel in there, the blue channel in here, and then here you take the top right corner, here the bottom right corner, etc., and you define the workflow. And of course, this is a very simple description of what you actually do, but you get the point. And for each of these nodes, you define numbers. Well, you don't define it. Basically, you train the algorithm so that it's able to define these numbers by itself. And the ensemble of those numbers is what we call weights. So at the end of the day, you end up with two things: the structure of the operations or type of operations that you do, if it's multiplication, sums, division, kernel operations, convolutions, etc., and the weights, which are basically the numbers that you put on top of those multiplications and stuff to process your specific image. Does that make sense? Well, so what we have been doing in the previous example is nothing related to this. We're doing similar operations like convolution and stuff, but what we are doing is a very specific workflow that in each of the patches that we have in the image itself, we're running this sequence. And as soon as that sequence gives us a no, then we just go out and run to the next one. But in the case of machine learning, or sorry, in deep learning, we will run the whole algorithm in each of them. There's no early stop, nothing like that. You run the whole thing, and then at the end you say, okay, that weird number that I have at the end, is it a dog or not? And that's why you train your algorithm for. The beauty of it is that since you have a lot of simple things, but you have a lot of them, at the end of the day, just by chance, you end up designing it properly. And that's the magic of it. Okay. So that's what we're gonna do now, actually. So if you, from what I understand, you can use strips learning network to test classifiers to stack them formula. Yes, exactly. So you could do as Daniel is saying on the chat. Let me go back to the desktop. This time I won't forget. So welcome to YOLO. YOLO is not you only look one, not you only live once, but you only look once. And it's an algorithm that basically is intended for real-time object detection. Of course, for those that have a proper GPU, not like mine. But the idea is that you are doing these processes of detecting objects, but also being able to tag them and identifying whether or not they are a dog, a cat, a car, or a person, for example. For that, you need three things. And that's when you download YOLO, you will find that you need three things. The first one, let me find instructions, get the weights. Actually, no, we can see it in here. So first you need the YOLO algorithm, so the algorithm itself. Then you need what we were saying, the weights. Well, this is the file that defines for this specific training that the author of the algorithm did. What are the numbers that you have to put into the algorithm to better detect what the author did? You can change this and you can train the model yourself, and there are instructions to do so as well. The YOLO configuration, so let's say what we call the hyperparameters of the algorithm. So if there are decisions that we put into the algorithm, for example, how many times or how many millions of iterations we're going to do to train, how fast are we going to do the learning, what is the threshold, so that we decide that something is a something or not, etc., etc., etc. And of course, this file is very big as well, and that's also the magic of for the person that describes the algorithm. And as you see here a lot of convolutional layers. These are like convolutional operations, but in images. And you see that are, for example, I don't know, 128 filters, etc., etc. That is like the structure of the network itself. And finally, what is it? Here. So we have the numbers that we put, so the weights. We have the configuration of the algorithm, and of course we need the binary. And there's just an extra thing in this case, which is called the names. And in this case, there's something called Coco that is stands for common objects in context, sorry, which is a data set of things that just can appear in images and with names, let's say. And the person that uses, the guy that made this algorithm basically used the COCO names, which is a list of names that we're going to use to identify what those things are. So for example, in this list, you will find COCO names. Let me open it so that you see extras, COCO names. So you see, these are the things that we are able to identify with this algorithm. Baseball bat, a skateboard, wine glass, a fork, a TV monitor, a microwave, etc. And these are objects, common objects, that you will probably find them in an image, and therefore that's what you are going to be able to identify, or that's something that can fall into one of these buckets, let's say, of what it possibly could be of what we are seeing. The important thing is that these things have to be somehow in context.
Es muy surrealista.
Mute.
Es muy surrealista.
Mute you, Benjamin, sorry.
Sorry.
So in this COCO dataset, these are people that basically contribute to a common dataset and basically tag things in pictures and images, and probably you are doing that for Google whenever there's a CAPTCHA that tells you, is this a traffic light or this is a motorcycle? And you are training their own common objects in context dataset for their own algorithms, but in this case for free, which for example I don't like. But basically you are contributing to one of these datasets, and basically you're saying that, okay, this image, for example, this bear, in this outline, this is a bear, and I tag it and I say this is a bear, or here are two dogs, or this is a plane, or this is a motorcycle, and on top of that there's a person, and this is a moped, and on top of that there's a person, this is a chair, this is another person, this is a bus, these are people, trains, etc. So you do that on, and these are the images that you will possibly use for training your algorithm. Luckily, someone else did that for us, and we have already the algorithm trained, and we already have the names that our algorithm is able to detect. Now, of course, there are thousands of millions of algorithms that do this. I recommend that you, if you are interested on this, you have a look at this source, Fast AI. Maybe you want to go into Kaggle and do a competition. Fast AI is a very good resource if you want to learn about deep learning. They have open courses on machine learning and deep learning for image recognition, sequential models, and many other things. And they have videos. Is University of San Francisco, I believe, and the guy that teaches, his name is Howard something Howard, and he's very good teacher or professor, and basically wrote most of Fast AI, which is a framework for artificial intelligence. And there are a lot of resources here for you to see different networks and combinations of networks. I'm just going to give you one, which is YOLO, but there are thousands of them, like ImageNet, RetinaNet, CNN, convolution networks, HomeNet, Fast, whatever. Okay, there are thousands of them, and you can read about them in here. And you can see examples in here in Kaggle. Kaggle is a platform that has competitions that they release, for example, competitions for better, for example, tagging dogs in pictures, or real data sets, for example, predict what is the effect of coronavirus in 20 years, I don't know, and try to determine the best algorithms. And then there's a very big prize. For example, you can enter the competition, and if you end up in the leaderboard in the first or second two places, of course, you're going to have a job. because a lot of companies are looking for people in these competitions. But of course, you're gonna get a monetary prize, like $20,000 or something like that. But also there are a lot of discourse, a lot of discussions, courses, and notebooks. So Jupyter notebooks, so that you can see how people do algorithms and these type of things. With data, I don't know, introductions, tutorials, etc., which is a very good resource. But we're just going to focus on one, as I say. So let's run. Let's run the YOLO. We are going to have a look into the code first. YOLO. This one has. This relates to the question by Pablo earlier. So we have to give it an image. We have to give it where the YOLO directory is. In this case, I have it in this folder called extras. And in this folder, I have the configuration of the algorithm. So the convolutions, the different filters, operations that I have, the weights that I downloaded from the author's website, but there are a lot of configurations and a lot of different trainings from other people, and the COCO names, okay? So that's what YOLO is. Confidence is the algorithm, of course, is not certain about whether that's a something or not. And it will give you a confidence threshold of like somehow similarity of whether or not that is a dog or not. And it will give you a number from 0 to 1. 1 is absolute certainty, 0 is absolute certainty that is not. So if you want to decide based on a minimum threshold, you can say that it's a 0.5 or can be higher and say, okay, I want to ignore everything that is below 0.9. And I just want to know something that is you're certain that is a person, for example. So you put that in confidence. And that's pretty much it. We are gonna input then the image. So let's take the cars, for example, and let's take YOLO in extras. So you just have to give the path for the folder. So it's loading YOLO. This file, I think, is the weight. I think is like 200 megabytes. And you see, this is the result of the image analysis, and it's finding all these little cars with a confidence of 0.96, 0.97, 92, something like that, in all of it. And it gives you the bounding box and the ID that has to be within the COCO names and the confidence interval. And it's also giving us the traffic light in this case, because there's a traffic light in the COCO list. Okay. Let's close this. Let's load something else. Let's load, for example, the Eagle example. Loading YOLO. It took 2 seconds. Boom, a bird, and with a 0.99 confidence. The beauty of this is that you can do this not only in images like this, but also on video. And that's what we're going to do in a second. Let's put something a little bit more complex. Let's see what I have in this folder. Actually, let's put one of these. Let's put one of these images from earlier. Let's see what happens. So capture slash frame. Let's put, I don't know, this one. Loading 1.9. Oh, jumped into here. Picture, person, and boom, a book in there. It detected that there was a book. But you see that the book confidence is very low because the image is quite blurry in there, but this is quite obvious for the algorithm. So it's a confidence of 0.9974, which is damn high. It's like almost certain that that's a person. And the image is not like very like perfect image. I could be looking at another position or looking to the right or whatever, and it could be, and it would take exactly like a very similar decision. But you see, one thing here is that one frame takes around 2 seconds. Of course, you can optimize this with many things, more threads, GPU, etc. But that this is like the core thing, that this is somehow lower than the other algorithms that we were seeing earlier. Let's see what it does with video. And this is where we are going to end today. And then I will give you a lot of resources that we can explore further. And if you have more questions, we can probably look into more things and do other type of classifications or these things. But let's take a video. And the video we're going to take is the one of the dancers that I showed you earlier. So there's like a video that is moving, people in weird shapes, weird colors, doing weird things. And we're going to just take a chunk of the video. We're not going to take the whole thing. You see that the camera is moving as well, so it's not like the perfect setup. It's not a static image with very good quality. It's not the case. And the chunk that we're going to take is this one, okay? So it is this dance short part. And you see that even in this part, you see that there's like an acceleration of the video that has like a much faster frame rate, or that is like sampled somehow. And let's input that. So YOLO. So I need to pass the YOLO extras. I need to put the input. For that, we're going to take the video. And we're going to take dance short. We're going to output that. It's not going to do it real time on the video. What it's going to do is export a video with the tags on it. And we're going to put it into a video that is going to be in videos output class dot AVI. So it's loading YOLO. There are 128 frames in the video, and then it gives you an estimation. And this is going to take a little long because 1 second, so one frame is 2.5 seconds. So all these frames will give us more or less 5 minutes. So I'm going to just skip that because I did this earlier. And we're going to see what the result looks like. So you see, just pause that. You see that in each of the frames is finding a bounding box, giving you that there's a person in here, telling you that that's a person with the confidence of that person. And you see that there are 3 guys in this image, each of them with a very weird position. And in each of them, it successfully got that there's a person in there. And person, you see there was a mismatch in here. The legs of this guy said that it was a dog. And that's obvious, like it's a very weird shape. And for that, that's why you probably would have the threshold to define like, okay, is there something below 0.8? Then I just discard it. And go frame by frame, person. Even in here, you see in these frames that are shaky, that I don't know how you call these effects, and probably you know better, Benjamin.
I can't remember. Yeah, motion blur.
Yeah, something like that. But you see that there are like a lot of frames overlapping, and it's able still to identify that there are 1, 2, 3. This one probably the arm is covering it, and this one is certainly very difficult to identify that as a person, but it does pretty well.
And do you tell it find only people in the video?
Yeah, exactly. So it's going to tell you that there's a person, or there's a something, and that something can be whatever that is in the list of the coconates, and where that is.
Why does it not, for example, detect the trees behind or something like this?
Well, I guess, I don't know, actually. Probably the confidence interval is 2 to 0.5. Let's actually, we can leave this running in the background. Confidence is threshold. No, confidence 0.3. Let's just leave running in the background and let's see if it detects them. Of course, you need to like of the cells, so you're going to have a very good result, but you can tweak a little bit in here. And also, of course, like I'm giving you a very brief introduction. There's like a way to make this a little bit better. So what is this doing? We're doing this in 120 lines of code, of course, calling libraries and stuff, but we are inputting arguments, loading labels, or in machine learning, these things are called labels or coco names, which are the coco names, sorry. We are loading the algorithm, so the weights and the configuration with this instrumentation, with this thing. But by the way, this is already into OpenCV as of OpenCV 4, I think. It's analyzing the first image. Let's avoid that a little bit. Detection, okay. So get unconnected out there, sorry. Argmax, confidence. Okay, so here, so in this, so for each of the outputs that we get and for each of the detections, then we get the scores, we get what that is and the confidence of that. And if the confidence is larger than where we defined in the input, then we will take a bounding box of that and make a box around it and define the center and make a box that we will put on top of on the frame. And then we're gonna put, let's say the box, the name and the classified. And this box, of course, then you can do some more complex things. And for example, go into what we were seeing in here. And as soon as you get the box, the bounding box of the person, you can get the middle bottom point. That is going to be on the ground if you are always certain that that is you're going to always see a person, full person. And with the same technique of homography, since you have each of the frames, if you have key points in your video capture, for example, this rectangle here, that serves as a reference, then you can do transformation, a perspective transformation, and see how this person moves around in the space by just one image fit, and not needing depth in an image, but just detecting the person and having key points around. And this can be useful for many other things, for example, to detect not only persons in here, but cars in the street or whatever. Okay.
Oscar, does this run in real time if you have a GPU?
If it can run in real time if you have a GPU, yeah. And there are optimizations for that. I'm not fully sure, but I think that you have to compile with CUDA framework. So if you are interested in doing this, you should start researching on about CUDA, which is an NVIDIA, let's say, architecture for doing operations in the GPU. And you can compile open frameworks to work better for CUDA, and then being able to run this much faster than what you've done in my stupid, like, well, not stupid, but very slow processor. In this case, I'm not using the GPU in my case, because I have a very bad GPU that is worse than my processor. So so that's basically it. And of course, you can do these things in real time, but you need to invest in hardware. And probably sometimes you can invest in hardware that doesn't have to be in your computer. You can run this externally with an external device, and then so do the processes in an external GPU and bring it back to the main computer or something. But yeah, for doing this in real time, you have to optimize this a little bit. But as you see, this is already quite powerful. And let's see actually the result of our video output. Let's see what happened when we change here. So it didn't detect the thing, anything like a tree. There's a horse at some point.
He says he's pretty sure it's a horse as well.
Come again?
He says
It
he
was
was
pretty.
90% sure it's a horse.
92% sure, yeah, exactly. But of course, like these things are a little bit of tweaking with the algorithm itself. And if you know that there would be no possibility to have traffic lights in a certain environment, then you will delete those things so that you don't have to make those decisions. You see here that the output is very fast actually. And even it found a tie at the very end of the frame. And the important distinction with the other part, of course, is the speed and stuff, but that we are not defining what we want to find, like specifically. We have a training process, and of course, the better and the broader we train our algorithms, the more things we are going to be able to find. But we are not telling the algorithm that you should do this operation and this operation and this other. It's learning it by itself, at least the number that it puts into it, and then getting those outputs and deciding based on those outputs. And I think, well, that's pretty much everything I wanted to share. Just want to give you some references and probably some examples at the very end. There's something called model SUS, which is a compilation of models that people have put together for you to like accelerate things, or just like people that have worked and released their model. So there are Cafe is a framework for machine and deep learning. OpenVino, it's visual. It's, I think, computer vision. It's OpenCV, but I think they have a collaboration with Intel. And they do this OpenVino toolkit or repository, and then you have like a lot of models that you can download for each of your needs. Let's have a look into here. Intel and public. So all these models are models that you can probably find and use yourselves to do computer vision stuff. So those are model SUS. A lot of references here. I give you some more things about descriptors and for example, the Viola Jones algorithm. I find this repository very interesting. Computer vision basics in Microsoft Excel. There's a bunch of Excel sheets that you can use to learn a little bit how images are represented and some different workflows. So for example, how can you put an image in numbers, colorize that into Excel and see how the image looks like the base of the image, and then basic operations onto that. This is done, I think, by Amazon. So people that work in Amazon or things like this. So the same things we were applying, but in let's say more common framework that is Excel, that everyone can get to understand better. And here you see like homography principles, alienation, filtering, detection, etc., etc. Okay, just done in Excel. More stuff. Pillow or PIL is Python imaging library. PIL, I think, is the original one, but I think the development stopped in Python 2.7, and then someone forked it, and now it's called Pillow. It's for loading images and doing images operations into Python, not explicitly related to algorithms for detecting things and stuff, but for doing like more like easy type of things. And finally, because I'm sure that you will be looking into this at some point, is how do you work on a Pi? How do you compile OpenCV in a Pi? What things you can run or not? What are the versions and this type of thing. In the repository as well, there's one guide in a PDF. The one guy, this guy Adrian Rosebrook, he has a Pi image searcher blog. It's very good, but you have to sign up for getting some code and stuff. But it's okay. He gives a lot of info, like generic utils for image processing. A lot of libraries, not only OpenCV, but for example, scikit-learn, which is machine learning in Python, TensorFlow, which is Google's framework for machine learning, Keras, which is a wrapper for machine learning as well, and deep learning or neural networks in general that can run different backends, as for example, TensorFlow, scikit-image, which is the image recognition or image processing algorithms in Python, and a lot of references, and many tutorials that he has on his blog, but compiled in a very nice guide. So for example, if you're looking into image processing or facial applications or OCR, this is something very interesting, for example, for detecting characters in documents. When you scan a document, you can detect if there's a word or a letter or things like this. Video, image search, working on a Pi, and extra stuff. Okay, and more references. And of course, this is a very like fancy and complex topic. We can do more sessions about this if you want. But I think like this is a good introduction, and then feel free to ask me about these things. I think, I don't know, probably Roger has also played with a lot of things in the past. He showed me some examples with Twitter and these things. If you are willing to do some projects or stuff, we can certainly collaborate on it. And of course, I can give you references. And that's pretty much it. I think we exceeded the time by 40 minutes, but well, for me, it's okay. Do you have any questions? Stop sharing the screen. Good morning, Arman.
Yeah, I have to stay in my room because they have a meeting outside.
Okay.
I just shared with you guys in the chat some PDFs I downloaded. I think it was also from PyImage. There's one with a few tips and tricks on Raspberry Pi. It's for Raspberry Pi 4, but I think it's gonna work with Raspberry 3. And I was reading it and I had a doubt, Oscar.
Mm-hmm.
How do there are some USBs that help the neural networks, I think, like the one from Google Coral and the NVIDIA compute stick.
Sorry, you muted and I.
Sorry, it was my fault. Yeah, so I was showing you some PDFs, but when I was reading them, I had a question. I saw that there are some like USB sticks that you can connect to a Pi or a computer to make it work better when working with neural networks, or like there's one called Intel Neural Computer or the Google Coral.
Okay. I don't know about them, but for sure, there are these things. There are some already that are like in form of an Arduino itself, or more, let's say, commercial type of things. I don't know about them. I've never used them, so I would have to research a little bit about them. In the lab, just so you know, we have Intel. What is this called? Intel board. What is this? We have a bunch of them. is called Galileo, the Intel Galileo. And we have a bunch of them. So if you're willing to explore this as well, I think you can. It probably is based on the same thing. I'm not sure. We have to research a little bit of it on this, but I know that we have them. And I know as well that if you want to do it more in a, what you already know with an ESP32, the ESP32 camera. I just shared with you this one in there. In Hackaday, the new ESP32 has like a small Linux running in it, based on RISC-V, and it can do like quite a bit this stuff with cameras and machine learning as well. And there's a review about it. It's not yet released, but soon it will be. If not, I will put the Galileo. So if you want to not buy the ones or anything, and you can use the ones we have in the lab when we are able to come back.
Perfect, thank you. Yeah, I was just curious about how it works. By now, I'm just gonna order the no PR camera to start trying with my Raspberry.
So I'll put this in here. Okay. Any more questions? Was this useful for you? Or at least interesting? Stop recording.